Hi everyone. Today let's talk about sessions 8.5, the ratio, root, and comparison test. So let's review this chapter. We talk about sequence and series. So our main goal is given the series, and then we want to figure out whether the series converges or diverges. And then what are the special series we learn about? We learn about the geometric series and the telescoping series. So for those series, we actually have a formula for it. Like for geometric series, we look at the absolute value of the ratio r. If that absolute value of the ratio is greater or equal to 1, then we know the geometric series diverges. If the absolute value of the ratio r less than 1, then we know the series converges to the first term over 1 minus the ratio. How about telescoping series? Okay, we have 3 steps. The first step, identifying a sub k to be a difference between 2 terms. Okay, and second step, compute the first n terms the partial sum, s sub n. So that's a1 plus plus a sub n. And you see there are a lot of cancellations. Okay, so half of the term of a1 will survive and half of the term of a sub n will survive. Okay, and which half of the a sub n will survive? The small term with the bigger index will survive. Okay, and the third step, you let n goes to infinity. Okay, and then the limits of the sequence of the partial sum is actually the number that the series converge to. Okay, if you get infinity, then we say the series diverges. Okay, and then in sessions 8.4, we talk about the divergence test and the integral test. So from now on, when you are working on a problem that asking you to find so to determine whether the series converges or diverges, the first step is you compute the limits of the sequence. If that limit is not 0, then you can say series diverges by divergence test. However, if the limit of the sequence is 0, we will go to the second step. The second step, while we look at the series, is this a geometric series? Is this a telescoping series? Is it look like an integrable function? Yeah, integral function means there are some factor or terms, it looks like the derivative of the other factor. Like 1 over x is the derivative of ln of x. Okay? And then we can use integral tests okay, for that series. So today we're gonna learn more tests. So after this chapter, I will make a summary. It's like a map. You know, like what's the first step, second step, and which kind of series we can apply which test. Okay, we'll make a summary and comparison at the end of this chapter. Okay, so big idea. So there are some other tests besides integral tests which help us to determine the convergence of an infinite series. Big skew, you should be able to apply ratio, roots, and comparison tests to appropriate type of infinite series to show whether it converges. Okay, so the first test we talk about today is ratio test. So what is ratio test? Okay, let the series a sub k be an infinite series with non-zero terms, and we let r be the limits of the ratio of the next term divided by the previous term. So this is a ratio between 2 successive terms. Okay, and if the ratio is less than 1, greater than equal to 0, then the series converges. Okay, if the ratio is greater than 1, the series diverges, so including infinity. Okay, if the ratio is 1, then this ratio test is inconclusive. It means we should pick another test to use. Okay, So this idea is by the geometric series. You remember the geometric series? Okay, geometric series converges if absolute value of r less than 1, and it diverges if absolute value of r greater or equal to 1. So this is very similar. So if the ratio of two successive terms has the limits r, then at the end, it really looks like a geometric series, okay? So that's why if r, so you realize that here, r is the absolute value, so it's always positive. And if the r is less than 1, the series converges. So it agrees with this concept, okay? And then if r greater than 1, then the series diverges. So it agrees with this one, okay? With the geometric series. But however, because r is like the limits of the ratio of two successive terms, it's not like equal. It's not exactly like it's not exactly the geometric series. It just acts like that. So that's why when r is 1, this critical point, the test is inconclusive. Okay, so usually in this case, we should use other test. So in the exam, all the series given, you should be able to tell whether it converges or diverges with the appropriate test. Okay, that should be the case that you would say, oh, inconclusive, no conclusion. No conclusion means you used the wrong test. Okay, you should pick other tests to apply to that series. Okay, so that is ratio test. So let's go down and work on some examples, okay? So example 1, use ratio test to determine whether the following series converges. Okay, so let's see. How about let me use purple? Okay, or maybe let me use black and then for the important parts I use purple. Okay, so first of all, let's call this is a sub k. Okay, the first step always computes the limits of the sequence. Okay, I call it a sub k because I don't need to copy the whole thing again, right? Okay, so if the numerator, we have 10 to the k and the 3k plus 4. The denominator, we have the k factorial. Do you remember the growth rate sequence we learned in the sessions 8.2? Okay, who's the slowest? That is the natural log, right? So natural log is slowest. And then we have the power function or polynomial, okay? And then next we have the exponential function. So this exponential function, your base can be e or can be other base. And then we have the k factorial, and then the fastest is k to the k. Okay, so always keep this growth sequence in mind. So here, the numerator is like this guy, okay? And times 3k, okay? Plus 4. So it's like this guy times this guy. But the denominator is this guy. So which one is faster? Wow, the denominator is faster, right? Okay, so I also want to put it here. So we have the numerator. Okay, numerator over denominator. Okay, so if numerator grows faster, okay, then the numerator over denominator will go to infinity. Okay, if the denominator grows faster, then see your denominator getting bigger, so the limit is 0. Okay, so here you can see because k factorial grow faster, so then we have the denominator grow faster, so the limit is 0. Okay, so that is how we think. Okay, that's the first step. If we get 0, then we go to the next steps. Remember, if you get non-zero number, you say, oh, diverges by divergence test, then we stop right there. But here, because it's 0, we actually need to go to the second step. Okay, so when do we use ratio test? So we usually use ratio test when you see, okay, so use ratio test if you see the terms like e to the k, k factorial, k to the k, okay? When you see some these terms, you can think about the ratio test. Okay. All right, let's continue. So use ratio test. Okay, then we're going to compute our R. Our R is limit of the sequence, limit of the ratio, okay, of the two successive terms. So this is AK plus 1, this is A sub K. What is that? Well, first of all, because in our example, all the terms are positive, so we don't need the absolute value, okay? But in session 8.6, we're going to learn alternating series. So then the absolute values means we just look at the positive factor of it. Okay. We will talk about more in sessions 8.6. Okay, so what is A sub K plus 1? Well, it means, okay, it means in our formula, we replace k by k plus 1. So here we have 10 to the k plus 1, 3 times k plus 1. Don't forget your baby parentheses, okay? And then we have k plus 1 factorial. Okay, this is A sub k plus 1. How about A sub k? So A sub k, we have 10 to the k, 3k plus 4 over k factorial. Okay, that is our formula. Okay. All right. So next, remember if you have okay, so remember if you have like A over B over C over D, then that is A over B times D over C, right? So this is like A, this is like B, this is like C, this is like D. Okay, so that's why when we put it down, we get the A, so 10 to the K, but actually later on I will try to cancel. So here I also want to split them. So 10 to the K plus 1 I split as 10 to the K times 10. Okay, so 3k plus 1 plus 4. So I can actually distribute it. So it's 3k plus 3 plus 4. So that is 7. And then k plus 1 factorial. How do I split? I split as k plus 1 and k factorial. Why is that? You can think about what is 6 factorial? 6 factorial is 6, 5, 4, 3, 2, 1, right? So it's 6 times, 5, 4, 3, 2, 1 is 5 factorial. So that's why whenever you see k plus 1 factorial, k plus 1 and then the next number is k factorial. However, if you see 2 times k plus 1 factorial, that is 2k plus 2 factorial. So when you split, you want to split as 2k plus 2, 2k plus 1, and then 2k factorial. So you continue and to write the numbers until you reach something you want to cancel in the future. Here we want to cancel with k factorial. So that's why when we see k, stop there and put a factorial there. Okay? Alright, so, and next. The C we have 10 to the K, so we put C at the bottom. So that's why we have 10 to the K and 3K plus 4 here. And the K factorial, that's like the D, we put it on the top. Okay, now let's start to cancel. Okay, so let's cancel. What can we cancel? Well, K factorial, we cancel it. 10 to the K, we cancel it. And that's it, right? Okay, so let's see what are the terms. Okay, so we have 10, 3K plus 7. The bottom we have K plus 1, 3K plus 4. Well, this is rational function, right? So the dominant term of numerator is 10 times 3K, so 30K. The dominant term of denominator, the top one is the dominant term of numerator. The bottom one is dominant term of denominator is K times 3K, so 3K squared. So that's why we know when K goes to infinity, the dominant term is dominant. So we just look at the dominant terms. We can simplify them. So we have 10 and over K. Wow, what happened? What happened? So we actually get, when K goes to infinity, this is 0. Okay, let's go back to our ratio test. If R is 0, we are at this case, so the series converges, okay? So, by ratio test, our series converges. But because we already say ratio test already, okay? So we don't need to mention again ratio test. But if you didn't say on top, here you should say by ratio test, series converges. Okay, everybody? So that is the solution of example 1, part A. Okay?